We know from the previous class that the black body radiation and photoelectric effect shows that the electron, that means which is the part of the light, it is particle in nature, and in the other side, whether this light considers the phenomena of interference and diffraction, that means the light shows the property of the interference of the phenomena and diffraction. So then it will be considered as a wave. So from these two phenomena, in one side is the black body radiation and photoelectric effect, and other side for the wave nature of the phenomena of interference and diffraction, the light has the dual characteristics, both particle and wave-like properties. So in this way, we can consider that the dual behavior of this electromagnetic radiation. So whenever the radiation interacts with the matter, then we will consider as a particle, and when this electromagnetic radiation considers the interference and diffraction, then it will act as a wave-like. And this concept was totally aligned in the way to the scientist thought about matter and radiation. And this concept of the dual behavior of the electromagnetic radiation, it takes lots of time for its validity. That means after long time, this phenomena is convinced for acceptance. And it turns out, as you will see later, that some microscopic particles, that means electrons, has both the wave particle duality. Now we will solve some small quantitative calculations. It is very useful for exam. Calculate energy of 1 mole of photons of radiation whose frequency is 5 multiplied by 10 to the power 14 Hertz. We know the equation E is equal to h nu, and h is the Planck constant, and its value is the constant value 6.626 multiplied by 10 to the minus 34 joule second. We have to remember, always remember this. And nu, in this case, what is this frequency? Nu means frequency. It is the 5 multiplied by 10 to the 14 per second. It is given. So E is equal to h multiplied by nu. This value is there, and ultimately E, the energy, capital E, its value is the 3.313 multiplied by 10 to the power minus 19 joule. And this is for the single electron. So if we consider the energy of photon for the 1 mole, because here we have to calculate the energy of the 1 mole of photon, then we have to multiply it with the Avogadro number. Avogadro number is 6.022 multiplied by 10 to 23 mole inverse. Avogadro number also we have to remember always for this calculation. So if we multiply the E for 1 photon with the Avogadro number, then final result you can see here. The energy of 1 mole of photons is 1.0 199.51 kilojoule per mole or mole inverse. Next problem. Now the second problem. A 100-watt bulb emits monochromatic light of wavelength 400 nanometer. Calculate the number of photons emitted per second by the bulb. So first we'll see what is the power of the bulb. This is the 100 watt. Now unit will change. Watt means the joule per second. So power of the bulb is the 100 joule per second. And from the general equation, we know again the energy of one photon E is equal to h nu, and nu is the frequency. This is, we know, the velocity of the light divided by its wavelength. So E is ultimately hc by nu. Why we change this equation? Because in the problem wavelength is given for the light. So now if we put the value for the Planck constant h, 6.626 multiplied 10 to the power 34 joule second, and it also multiplied by the velocity of the light, which is 3 multiplied by 10 to the power 8 meter per second, and divided by the lambda. Lambda already given in this problem. It is the 400 nanometer. That means if we consider in a meter, then 400 multiplied by 10 to the power minus 9 meter. And ultimately the energy of one photon, after calculation, it will be the 4.969 multiplied by 10 to the minus 19 joule. And then the number of photons emitted. How do we calculate? Because the power of the bulb, we know the 100 joule per second. This one multiplied by the energy of the one photon. Then we will get the number of photons, and the final value will be 2.012 multiplied by 10 to the 20 per second. That means per second 2.012 multiplied by 10 to the 20 photons was emitted. Now problem number 3. When electromagnetic radiation of wavelength 300 nanometer falls on the surface of sodium, electrons are emitted with a kinetic energy of 1.68 multiplied by 10 to the 5 joule per mole. Now, what is the minimum energy needed to remove an electron from sodium? And what is the maximum wavelength that will cause a photoelectron to be emitted? So in this case, we know the basic equation E is equal to h nu, and when the nu is equal to c by lambda, then E is equal to hc by lambda. C is the velocity of the light, h is the Planck constant, and lambda is the wavelength. In this case, the wavelength 300 nanometer. So if you put the value for the Planck constant, 6.626 multiplied by 10 to the minus 34 joule second, you have to remember always the Planck constant is value, and multiplied by the velocity of the radiation. What is the velocity of the light? Then it is the 3.0 multiplied by 10 to the power 8 meter per second. This part also you have to remember always this value, and divided by the wavelength lambda. So lambda is the 300 nanometer. If you consider in the unit meter, then it will be the 300 multiplied by 10 to the minus 9 meter. Then after calculation, the energy of the photon, it will be the 6.626 multiplied by 10 to the minus 19 joule. So it is for the each photon. So energy of 1 mole of photons, then you have to multiply with this value with Avogadro numbers, which is the 6.022 multiplied by 10 to the 23 per mole. This Avogadro number also you have to remember always for this calculation. And then the final value for the energy of 1 mole of photons, it will be the 3.99 multiplied by 10 to the power 5 joule per mole. Now it is the total energy of 1 mole of photon. So you see the kinetic energy is 1.68 multiplied by 10 to the 5 joule per mole. So if you want to get the energy which will remove the electron from the sodium, then you have to subtract this kinetic energy from the total energy. Then that means the 3.99 minus 1.68 within first bracket multiplied by 10 to the 5. You see that in this case, in both energy is the multiplied 10 to the 5, and for kinetic energy also 10 to the power 5. So we make it common. So the value ultimately it will be the 2.31 multiplied by 10 to the 5 joule per mole. So now again, what is the minimum energy for 1 electron? So it is this value, minimum energy is for 1 mole. So if we calculate the minimum energy for 1 electron, then this value will be divided by again by the Avogadro's number 6.022 multiplied by 10 to the 23. So ultimately the value will be 3.84 multiplied by 10 to the power minus 19 joule. And this much energy, minimum energy required for 1 electron to remove from sodium. So now we know the energy. So next step, what is the calculation, that what is the maximum wavelength? So if we know the energy, then again just we have to arrange the previous equation, this equation, when the lambda is equal to hc by E. So h we know, Planck constant, this value multiplied by c, the velocity of the light, and E now we know that 3.84 multiplied by 10 to the minus 19 joules. So you have to whole divided by the 3.84 multiplied by 10 to the power minus 19 joule. So ultimately the lambda, that means the maximum wavelength, it will be the, after calculation, 517 nanometer, and this 517 nanometer wavelength is related to the green light.